It's my great pleasure to introduce Albert Atserias. Albert is a professor at UPC Barcelona. He probably doesn't need an introduction, but I think I will give one anyway. He's a legend in complexity theory. For many reasons, he has two PhDs, one in proof complexity and another in finite model theory. I believe I got that right. And in addition, he has done excellent work in proof complexity, descriptive complexity, finite model theory, and building bridges between these areas of complexity theory and logic. And he has won many, many awards for his work. And today, Albert is going to talk about the past and present of descriptive complexity theory. So his take on the whole field. So without further ado, Albert, the floor is yours, please.
Thank you very much, Vijay, for the introduction, and thank you everybody for joining. So indeed, I'm going to talk about past and present of descriptive complexity theory. Initially, the title had future, but I cannot predict the future, so I removed that from the title. And many of the things that I'm going to talk about are survey, and they don't include results of my own. In fact, many of the things go back to before the time I was born, like, for example, the Turing machine. So my thesis in this talk is that descriptive complexity is really one way to see it is by looking at the model of computation in which we're doing our algorithms. So let's remind ourselves what the Turing machine is. So the Turing machine works at the bit level. So it has a tape where you have some cell that is the current cell. And then the control has a set of instructions, and the instructions that they do the usual thing. They read a symbol, and then they do three things depending on what the symbol is. They rewrite the symbol with another one, they move the head left or right, and they jump to another instruction in the instruction set. Now, crucially, the set of instructions is a finite set, so this is a finite machine. And it's operating at the bit level, and for that reason, many typically mathematicians tend to think that this is not a natural model because it doesn't have sufficient structure to be able to analyze it mathematically. So, but in fact, it's not the only model of computation that works at the bit level. There is a very closely related model, in fact, which is the Boolean circuit. And this is what Shannon, in fact, very early in 1938, this was his master thesis in MIT. He called relay and switching circuits. And this is a remarkable paper where he was talking about Boolean circuits and essentially the way we think of them today. So we have some inputs that take Boolean values, x1 to x5 in this example, and then you have some gates where you do some obvious computation. Take two inputs and produces another output, another bit as an output. And so one way to represent this computation here is by the set of equations that you see on the right. So every gate gets a variable, and then you express what is the effect of the gate on its inputs. And Shannon himself analyzed the circuits this way, and this is what we call in the satisfiability literature, we call it the Zeytin transformation. But maybe it should be called the Shannon transformation, because Shannon used this to actually reason about the correctness and about issues about the circuit, exactly using Boolean logic this way. All right, so these are two models of computation. They are extremely, they are very well connected one with the other. There are transformations from one to the other. But the thing is that both are bit-based. They are based on working with bits. And we now know, and we also already knew back in the 30s, but at the time, I mean, the notion of encodings was actually quite new, and this was one of the contributions of Gödel, that things can be encoded at the bit level, right? But we know that the data has structure. It's not, data is not just a bunch of bits. So data comes from something that we want to understand and analyze, such as graphs. It could be directed graphs or undirected graphs. It could be weighted. It could have hypergraphs where edges have more than two vertices. You could have graphs that have structure of a tree. partially ordered sets, even KCNF formulas, you can think of them as structured data. So in this example, we have the clauses on the left, in this case 3 clauses, and the variables on the right. You have a bipartite graph with 2 types of edges which denote occurrence. And the occurrence with red could mean, for example, that variable x1 appears in the clause in negative polarity, and green would mean that it appears with positive polarity. So even though KCNF formulas are quite a low-level representation of data, they are still more structured than just plain bit strings. Other type of data which we might want to manipulate are matrices, which also have some structure, and we'll get back to it later again. So if data has structure, then why do we break the structure completely and we turn it into bit strings? And that is actually a problem. And this was a problem that at the beginning of database theory, Code realized that there was this problem of how databases are represented. And he introduced the model of relational model of data, the relational databases, and this was as early as 1970. And the model is the following. So it clarified, well, it was a very clean way of representing data comparing to what was at the time. This was still before the time I was born, so I'm just reading from the papers. So what is the relational model? In the relational model, we have some relations, and this is your input. And what are relations? Well, these are just sets of tuples, where a tuple is, well, a tuple, so a bunch of elements from different domains. And these domains tell what is the type of this relation. This is how it's called. So here is an example on the right. You have a bipartite graph. You have 2 types of vertices from some string domain and vertices from some numeric domain, and then you have some relation between them. And that relation is the edge relation in the bipartite graph. So in this example, the three relations would be the set of vertices U, the set of vertices V, and the relation of edge E itself. Okay, so Code said, let's represent databases this way with relations. And in fact, he acknowledges that this goes back to Tarski when he has this algebra of relations, and he introduces the concept of relational algebra and crediting Tarski for it. So he says, okay, what can we do with these relations? We can manipulate them in some ways, right? So we can do intersection of 2 relations, provided they are of the same type. We can do union of relations, provided they are of the same type. We can do set difference. We can do Cartesian products, where now the types concatenate. And then there are 2 special operations. One is the selection operation. This is denoted by sigma I and j. And what this represents are the tuples in the relation T, where I and j component are equal. This is the equal selection. And then we have projections, where in projections, we have, again, one component. And what you do is that you remove the element in that component. So you take all the tuples in T and you remove that component. So we say that we project I out of the relation. So these are the operations, the basic operations of the relational algebra. And Code suggested that with databases represented in his relational model, data should be manipulated with this sort of operations. So now we can formulate what Code himself called relational algebra expressions. So this is again like some sort of a circuit. It's written this way to show the analogy. So but now the inputs are not bits, but they are relations themselves. So the whole relation is put as an input, and you have the basic operations inside. So these are expressions in this algebra of relations. And again, you can do the intermediate relations, and then you can measure the complexity of the expression by how wide these relations are, how many Cartesian products we do, and this sort of analysis that we will do. Good, so these are relational algebra expressions. And then, so Code related this to something quite familiar, which is the first order logic on a relational language. So he noticed and he proved that relational algebra can compute precisely the same relations from given relations. It can compute the same relations that you can define with first order logic. Intersection corresponds to conjunction, union corresponds to disjunction, difference corresponds to negation. This sigma, this selection is the equality relation, which we usually assume given for free. And the projection is precisely the existential quantification, where now these variables range over the domains of our data model. By the way, once you have negation and existential quantification, you also have universal quantification. One thing to notice is that relational algebra is variable free. There are no variables. There are no individual variables. So what you're operating with is relations directly. In particular, you're not doing any choices. So when you do an intersection, you apply the intersection to both relations, to every tuple in the relation. And when you do a projection, you apply the projection to every tuple in the relation. You're not working individually with elements or tuples of your structure. And this is important because choice-free computation is what we're after in domains like databases and in other places. And that's a bit my point here. So before I go to what descriptive complexity brought into the picture of complexity theory, so let me make one comment, which is the comment between uniformity and non-uniformity. So one thing to notice in the difference between Boolean circuits and relational algebra expressions is that a single expression or a single formula can serve all inputs of a given type. So here's an example. If you want to define for a given graph the vertices or the set of vertices that belong to a triangle, then you have this single formula. This is a finite object with 25 symbols or something, where you're saying X is in the relation that you're trying to define if there are two vertices that form a triangle, one of which is X. Yes? So that's a first order formula. And this single first order formula of finite set of symbols serves all input graphs. And these input graphs are now our input relations. So in this sense, it's a uniform model. But we could also imagine that we have a non-uniform model of computation, where we could have, for example, a different relational algebra expression for different input lengths. This is an approach that is actually quite useful, but it's not the one I'm following in this. And it's not the one traditionally followed in descriptive complexity. So, and because of today I want to focus on past and present of descriptive complexity, we're going to focus on the uniform model. These things are usually called queries. So this is a query on graphs. They are graphs because the types are vertices and edges. Very good. So uniformity versus non-uniformity. And now there comes the issue of computability with relations. So we have the model of data, and now we want to say, how do we compute with these relations? Well, we already discussed the relational algebra, but is it powerful enough? Is this model powerful enough? Well, Aho and Ullman discussed this, and among many others, actually, around the late 70s and early 80s, this was an issue of discussion. But I think this quote here is pertinent given Ullman's recent Turing Award. So I think let's see what Aho and Ullman said. The general consensus about the model of computation for relations is that one does not wish to have general Turing machine capabilities. So that's a bit funny thing to say. Well, you don't want to be a Turing complete. So, but there are reasons for that, and they go ahead and discuss the reasons for it. And reasons is these principles that they formulate, that they say that we want this computation to be order independent, for example. That's one thing we want. And what does that mean is that, well, the way the relation is presented to you, the order in which the tuples are presented to the machine should not affect the output of the computation. And that's important for databases, because you want representation independence of your queries. I mean, you want your queries to depend only on the truly structural data, not on the representation of the data. The second principle, which is actually quite related, and it's a bit hard to distinguish one from the other, but there is a bit of a difference, is the isomorphism invariance. So here, what they mean here is that if you rename the elements, then the output should only change up to the same renaming. In particular, and this is an important point, if a structure, if an input has a certain automorphism, if you can, meaning that you can exchange two elements in your structure and not notice the difference, then the output should also have this automorphism. So this is an important concept for preserving the abstraction that is already in the input. And you want to preserve, you want this relational structure. Okay, so this model of computation introduced, or these principles of the model of computation introduced in the 70s was the guiding principle for databases. But then complexity theory also had something to say here. And so Fagins Theorem, in fact, is earlier. And Fagins Theorem, the way it can be interpreted is as a way to say that the isomorphic invariant of the iso-invariant fragment of NP coincides precisely with existential second-order logic. So what is existential second-order logic? Well, you take a first-order formula where you have some input relations and some auxiliary relations that are quantified existentially. And this is existential second-order because this is first-order and this is a second-order relation. And it's existential because you don't quantify universally over second-order relations. So Fagins theorem is exactly this statement that I wrote here. And what makes it an interesting statement is that the thing on the left is really a semantic class, if you think of it as just by itself, because the fact that the non-deterministic polynomial time machine computes an isomorphism invariant property is not even a decidable condition. And this is not something you can impose on the machine by just putting a clock. For example, the fact that the machine runs in polynomial time is not a decidable condition either, but you can enforce it by just putting a clock. But here, isomorphism invariant is not something you can enforce by such a simple device. But in fact, you can enforce it because this class of existential second-order logic is a syntactic class. It's a syntactic, meaning that the set of formulas that you are allowed to use are clearly decidable set. So your devices are decidable. Okay, so this is characterizing a semantic class in terms of a syntactic class, and that's what makes it interesting. In one direction, the reason it works is that you have the power to guess these existential quantifiers. And the other direction from machines to existential second-order logic, in fact, is nothing else than Cook's theorem done in sufficiently abstract way so that you preserve the automorphisms. Good, so this is Fagins theorem, it's already covered, so let's move on. So here's the zoo. Nobody likes zoos, I think, or very few people like zoos, but I think zoos at least have a good thing. It's that at least they are not jungles, right? I mean, they are organized. So here's what we call logics zoo in the same way that there is the complexity class zoo. So let me give you a map of how to read this. So down here we have complexity classes from the complexity zoo. And up here we have a bunch of logics that correspond more or less to these classes. So for example, here in this cage, this green cage here, we have NP, which is completely characterized by existential second-order logic. And in fact, this characterization can also be done for the polynomial hierarchy, where you go to full second-order logic. You could even do it for p-space in exponential time by looking at proper, that certain extension of second-order logic.
Albert?
Yes?
Can I ask a very naive question?
Yes.
So when you say that existential second-order logic is the same thing as NP, like NP deals with languages and whether strings are in languages. So what are our strings in our languages? Is it like whether a structure somehow satisfies a sentence, or how should I think about this?
Yeah, good question. Thank you. So by this, what I mean is the language encoding the relation. So the inputs are really relations, but they are somehow encoded. And now what I want to say is that a language, so a collection of structures, meaning of relations, is accepted by your machine if the encoding is accepted by a certain machine. Okay, so it's the encoding itself. But what you want is that this machine is isomorphic invariant, meaning that two encodings of the same structure up to isomorphism should be accepted both or rejected both. So really, the thing goes through encodings. Encodings are as bit strings, but what you wanted is that these encodings are either, if two encodings represent the same structure up to isomorphism, then either both are accepted or both are rejected.
Okay, but I can think of this as like my favorite NP-complete graph problem. What Fagin says that there is like as logical sentence exists X and then some phi, which sort of nails down exactly the graphs that have this property that make them yes instances.
Absolutely, yes.
Okay,
yes.
Thank you so much.
Thanks to you. All right, so here's my zoo again. And so let me give you this thing. So we have first order logic down here and existential second order here. And we have, okay, so these question marks, what do I mean here? Well, I have question marks because we don't know of a logic that corresponds exactly to isomorphism invariant polynomial time. In the same way that we know a logic that corresponds to isomorphism invariant NP, we don't know one for polynomial time, we don't know one for non-deterministic log space. So it seems to be that there is a dividing line between P and NP into the possibility, or at least as far as we know today, of capturing precisely the isomorphism invariant fragment of that complexity class. For polynomial time, it's the most attempts. So I did this cage quite long because I wanted to show the fact that there have been several attempts. And the arrows that have a cross means that it's been proved that they are not equivalent. And the arrows that don't have a cross mean that they are just simulations. So there are two logics that are particularly important, fixed point logic and fixed point logic with counting. So fixed point logic with counting is the focus that I want to give here. It's quite close to polynomial time in a quite clear sense and well understood. So let's get into that. All right, so what is fixed point logic? Before I define FPC, I need to define FP. So FP stands for inflationary fixed point logic. Usually some people put an I in front, inflationary fixed point or fixed point just for short. What do we have in this logic? We have the usual things. We have inputs, we have equalities, quantification over elements into domains, Boolean connectives, and then we have an inflationary fixed point operator. What is that? Well, that's nothing else than iteration. That's what I wrote here on the left. So I have the usual things, input, selection, projection, Boolean combination, and iteration. So what does it mean to iterate? Well, it's this very simple pseudocode. You start with the empty relation, and now you form the relation of tuples that satisfy psi given the current relation, in this case, the empty set. And then while the new relation is not equal to the old relation, then you iterate. You update the new relation, and then you update the new thing to be what you had before, plus the new tuples that are satisfied, that satisfy psi. So this way you get new tuples and you iterate until this converges into some fixed point, and that's what you output. And one thing to notice is that because it's inflationary, because each time we are adding new tuples, this is going to converge, yes? And in fact, it converges in time, which is polynomial in the arity of the relation symbol R in this case, or X in this case. Sorry, polynomial in the size of the input with exponent that is the arity of this relation, because there are no more elements to be added than that number. And now comes the immerman theorem that you may have heard, which is essentially saying that the deterministic polynomial time can be captured by inflationary fixed point logic, except that there is a big if. And the big if is that it requires the domains to be ordered and to allow this order on the relations, on the domain elements. So once you have this if, then this is no longer a semantic class, because isomorphism invariance becomes trivial, because if the domain is fixed by an order, then there is nothing you can permute within the same structure other than just changing the names. So the automorphisms become trivial, and therefore it's no longer a semantic class. Still, this is a powerful tool, and in fact, we're going to see an application of it. But it's not solving the question of whether there is a logic for isomorphic invariant P. So the question that I want to ask is, why do we insist? People ask, why do we insist on ordered domains? Why is that so important? Well, for one thing, Fagins Theorem doesn't need this, right? While P seems to require it, at least as far as we know today, and therefore there seems to be a fundamental difference here that we have to understand. This was the problem of a logic for, or a language for isomorphic invariant P raised by Chandra and Harel. Another thing is that all problems of interest, as I already argued, are isomorphic invariant, even KCNF or KSAT and these sort of things. They don't depend on automorphisms. If you flip two variables and that doesn't change the structure of the formula, it stays this variable. Another thing is that we want to look at choice, because essentially having a linear order is like having a choice. You can always choose the least element in the order. You want to think of it as a computational resource in the same way that we think of random bits or quantum bits as a computational resource. And the question is, how much of this resource is actually needed for efficient computation? And the last thing is that there is a program here that I want to highlight, and that was the whole point of this talk. So before I get to the program, I need to say what is fixed point logic with counting and why do we need counting? So one thing is that fixed point logic cannot do basic arithmetic with the cardinality of the structure, for example. It cannot even tell whether the structure has an even number of elements. This was recognized early on by Immerman himself, and he said, okay, let's throw in quantification that allows us to count. In particular, he said, let's use a counting quantifiers of this type, where you say there are at least I elements X that satisfy psi, but now I is a variable that ranges over some special number domain, which we assume is given in the input, and we allow some arithmetic on this number domain. The whole point is that this number domain and the other domain, the domain of actual structures, are only connected through these quantifiers. So there is no way to order the elements in the given structure by the order that you have in this arithmetic, because there is no way to connect them one with the other. You don't have a bijection between them. So let me give an example of how you do fixed point logic with counting. You can do quite sophisticated things. This is a basic one first. So let's count walks in graphs. So suppose we're given a graph on some vertices. This is an adjacency matrix. You can think of it as a 0-1 matrix with indices, the vertices of your graph. And now how do we say that there is a walk of length 2? Well, that's the squaring of the matrix. So, or rather, we want to count how many walks of length 2 we have. So we sum over all W's or intermediate points, and then we take the product. Okay? One thing to notice is that this is isomorphic invariant. If you permute the W's, then because the matrix also permutes, then you're getting the same count. Now, once you can do paths of length 2, you can do paths of any power of 2 by iteration, and this is what you do with the fixed point iterator. By the way, here I'm counting exactly I by saying there are at least I and there are not I plus 1. So this is quite a powerful way to compute things. For example, so here is a list of things that you can do with fixed point logic with counting. You can do connectivity queries. This you can already do in fixed point logic. You can do 2SAT. You can decide the satisfiability of a 2CNF formula. You can decide whether a CNF formula has a bounded width resolution refutation for some fixed width. You can design Horn-SAT. You can execute unit close propagation, which is essentially the same as Horn-SAT satisfiability. So these are things you can already do with fixed point. Now, once you add counting, you can start doing things like perfect matching of bipartite graphs. And you can do matrix non-singularity over finite fields. You can do algebraic things. You can also do determinants over the rational numbers. You can solve linear systems of equations. You can do linear programming. You can do perfect matchings on general graphs. You can even do the ellipsoid method. So it becomes a very, very wide fragment of polynomial time for which we actually know how to prove lower bounds. So it can do all this, but at the same time, we can show that it cannot do certain other things. But the focus of this talk is not on lower bounds. I would be happy to give another talk on lower bounds and Ehrenfeld-Fréchet games and all that goes into them, which are beautiful results. But today I want to focus on upper bounds. So let me tell you how to do determinants, for example. So how do you do determinants in a way that preserves the isomorphism of the adjacency or of the matrix? So you have a matrix of rational numbers, and let's say they are 0-1 entries just for simplicity. They can be just any rational numbers. Think of an adjacency matrix. Now, the determinant of this matrix, you can express it by the usual formula. And if you look at it, it happens to be isomorphic invariant. But that doesn't mean you can compute it in polynomial time in isomorphic invariant way, because that's an exponential big sum. So the question is whether you can compute determinants of rational numbers in FPC. And here computing, what you want is to compute the value as a binary relation that encodes the binary bits, the bits of the input. So one warning is that Gaussian elimination, this is a fantastic algorithm that is used all the time, it's not good for us. It's not the choice, choosing a pivot is not something we can do, because when we choose a pivot, we're breaking symmetries. So Gaussian elimination is not available. But the nice thing is that there are alternatives. So Leverrier method, for example, if you are in characteristic 0, you can express the determinant of, the characteristic polynomial of the matrix with a recurrence. The coefficients of the characteristic polynomial can be expressed as a recurrence that depends only on the trace of the powers of the matrices. But the powers of the matrices we already said how to do in FPC, so it's available in FPC. And the rest is just a recurrence of some basic arithmetic that you are allowed to do in fixed point logic. What about the trace? Well, the trace is just the sum of the diagonal elements. And the diagonal is, of course, definable because it's just the selection of the entries of the matrix with equal indices. That's exactly the sigma. So you select the diagonal, you add them up. You add the whole diagonal. That's expressible in FPC. Therefore, you can express the coefficients. And once you have the coefficients, you plug 0, you get to the determinant of A. I'm a bit out of time, so no, I don't have time to discuss linear programming. It's a beautiful algorithm for doing linear programming due to Anderson, Dawar, and Holm. It's based on refining the ellipsoid method. I don't have time to discuss this. So it's a beautiful, beautiful algorithm. So instead of that, let me finish with a couple of slides of some directions of future work that I think could be done here. So there's a program here that one can put forward, which is that, okay, we have this very big fragment of polynomial time computation. It can do many things. It cannot, certain things it cannot do, like solving systems of linear equations over finite fields. So that it cannot do. But it can do for characteristic 0, it can do for many other things. So it's a big fragment. And now the program is to prove the predictions that complexity theory conjectures do, but do that, prove it unconditionally. And by the predictions, I mean that I don't pretend to prove the complexity theoretic conjecture itself, but whatever is predicted by this conjecture. So here is an example. So I put it in abstract terms, but you can put it in concrete terms. Unique games conjecture. Well, let's put it in abstract terms. Conjecture X says that problem Y is hard. Okay, that's exactly what the unique game conjecture says. So now you want to show that the family Z of algorithms, so a huge family of algorithms that you are interested in, things that come from proof complexity, things that come from optimization, sum of squares algorithms, whatever you have in mind. You want to show that this family of algorithms cannot refute the conjecture X, and you want to do it unconditionally, because this is predicted by the conjecture. So the way to do it is you show that the algorithms in this family Z are definable in FPC. And then by reductions, in the end, you can show that you can show that in fact these algorithms cannot solve this thing, and therefore, and you did that unconditionally. Now, for the unique games conjecture, there is some initial work by Jamie Tucker-Foltz. This is a very recent paper that is very interesting, and it doesn't solve the unique games conjecture for the algorithms of FPC. But it makes some good progress. For hardness of approximation, like max 3-SAT and max XOR-SAT and all that, we did it with Anoush Dawar a couple of years ago. And finally, one last example that connects to the next talk is the following. So again, within this program, suppose you want to prove lower bounds for a proof system X. What do you need to do? Well, one thing you can do is show that the proof search algorithm for this, the restricted complexity proof search algorithm for this is expressible in FPC. And in fact, this is one way, and Joanna Kremiak in her talk earlier in this series talked about this approach to proving lower bounds. And this is precisely the topic that Benedict Pago is going to tell us about in the next talk. So why would that be enough? Well, because you prove, so you want to say, suppose that a certain formula is easy for proof system X. Well, then this FPC formula would be able to find the proof because you showed that the proof search is doable in FPC. But on the other hand, you know that some formulas are hard to distinguish in FPC from unsatisfiable formulas are hard to distinguish from satisfiable ones. So it could not have had a small proof in the first place. So this way of proving lower bounds has actually been put to work, and I insist this is what Benedict is going to tell us about. So I'll stop here, and I think I'm a bit over time, so thank you for your attention.
Thank you, Albert, for an amazing talk. Questions, please.
I have a question.
Go ahead.
Or a comment. So Abitabul and Vianu and me, we introduced a kind of an intermediate model of a relational machine.
Yeah.
That in some sense, it really tries more to say, how do we compute those relations and without having to know logic, so to speak. So you basically says, okay, suppose we write programs that can use relational algebra. And then we are able to show kind of tight connections to this, to the logic.
Yeah, I'm aware of your work. In fact, it was there cited at one place, but I was running out of time, so I decided to reflect to go back to POT and to relational algebra. But I'm aware of your model, and yeah, it's definitely. In fact, in the abstract, I even talked about relational machines, and this is your terminology, relational machine.
Yeah.
So basically, you have a store of relations that you're allowed to manipulate through basically a Turing machine that has instructions that say what to do on the tape and what to do with the relations. And
right.
It's a beautiful model. It's useful.
Has not been very influential for some reason.
Yeah.
There's a question by Valentin. Is there a non-uniform version of FMT that can talk about circuits?
Yes, absolutely. This is an excellent question. It's something I wanted to talk about too. So I focused on the uniform model because that's how most of descriptive complexity in the early times was developed. But the non-uniform model makes perfect sense. And all the lower bounds, in fact, are for the non-uniform model. So why is that? So first of all, what is the model? The model is that now we have you can imagine you have a fixed point formula or even first order formula, it doesn't matter because you can look at them as unrolled. And you have one different formula for each input size. So for graphs of size 25, you have a formula. For graphs of size 26, you have another formula. And the only condition you put on these formulas is that they should all be in size bounded by some polynomial, for example, or some exponential even, or some sub-exponential function. And now the lower bounds for descriptive complexity, they work in the non-uniform setting because the way they are proved is by showing that you have two graphs that look very similar and yet they are indistinguishable by formulas of certain size or certain width, to be more precise. And that depends only on the size of the graphs. I mean, you don't need to have infinitely many graphs to play around. You have only two graphs of a certain size and you play the Ehrenfeld-Fréchet game to show that they are indistinguishable. And therefore, you can construct infinite families of such graphs, one for every input size, and therefore you get your lower bounds. Now, the thing is that the lower bound you get is for circuits that satisfy a symmetry condition. They are not arbitrary Boolean circuits, they are symmetric Boolean circuits. And this is the topic of my talk in a few weeks ago I gave in the seminar. And Anush Dawar also gave a talk on this concept of symmetric circuits. So we get lower bounds for non-uniform symmetric circuits, exponential lower bounds.
Thank you. Any other questions? So I had one question. If you may go back one slide or the last slide where you showed yeah. So I'm trying to understand what you're saying here. So you're saying that FPC is this restricted version. It doesn't completely characterize P, right? It characterizes some large fragment of P. And if you show that proof search for a proof system X is easy by showing that proof search is in FPC, then that would in turn imply that the size lower bound on proof system X, basically that's what you're saying.
Yes.
Okay.
What
Awesome.
would be a bit confusing is how can proof search be easy if they are all hard, right? They are all NP hard, more or less. Well, here, because I'm thinking of proof search for proof systems like bounded with resolution. There it's easy. I mean, the only thing is that it depends on the parameter. So you have, for width W, you get time n to the W. But that's okay, because we have lower bounds that are exponential. So if proof search in n to the W can be done in FPC with W variables, that's the terminology that is being used. So if you can do it with W variables, then a lower bound for W variables will give you a lower bound for width W. So all of these things actually match very well.
I had one more question. At the very beginning of the talk, you mentioned that the correspondence between relations and first order logic. And you said that the relational algebra that you showed there is variable free. Now, this would be true for finite relations, right? Is it also true for
yeah, so I forgot to say this is finite relations only.
Okay, yeah, that's
it's important.
Yeah,
it's finite model theory, it's finite relations only.
All right, okay, yeah, I mean, good.
Well, in fact, this very relation, this holds for infinite ones as well, but for infinite domains, but not everything goes through. So, for example, in this zoo, this is quite interesting. So least fixed point logic and positive least fixed point logic. So this is, you don't allow negations on the fixed point operators. So these two things in finite structures, they happen to be equivalent. So they are close. So we say that least fixed point is close on their complementation. But for infinite structures, this is not true. So this is a theorem by Immerman, by the way. It's a theorem of finite structures, of finite model theory.
Thank you very much. That was a very enlightening talk. Thank you, Albert.